Hi guys, Mr. Rocco here. I hope you're having a good weekend. I hope you're staying warm and you are preparing for the rather big snowstorm that's headed our way, starting tonight and over the next couple days. We're going to keep moving with the unit on weather, very appropriately. So let's talk about the three of the variables when it comes to weather and how they relate to one another. So we have temperature, pressure, and moisture, and how these relate to one another. So let's jump right in. You're all aware that warm air is less dense, right? Warm air ends up upstairs in your attic or upstairs floors of your house. So it says as air gets warmer, its density decreases, right? Becomes less dense, and it gets pushed up, right? What's pushing up the warm air? Well, cold air. That's convection, which we talked about last week. So the air's warming, it's getting less dense, and it's rising in the atmosphere. As it's rising now in the atmosphere, it's going up into less pressure. The higher up in the atmosphere you go, the lower the air pressure is. And so as this amount of air, this parcel, they'll call it air, is rising, it's because it's moving into lower pressure. The air can spread out. The molecules, the air molecules can move apart from one another. They can expand, and because they're moving into less pressure. So the pressure drops, and so does the temperature, right? It starts to cool because of the fact that the molecules are not colliding with one another as much. So as air is rising in the atmosphere, and because it's heading up into lower pressure on it, there's less pressure exerted on that air, the molecules can spread apart. Less collisions means less friction, less heat, and therefore the temperature gets colder. So rising air is going to expand and cool. And then it says the water vapor that's in this air, right? Some of that air has moisture in it. Well, that water vapor is going to now cool and condense. It's going to turn back into liquid droplets, and that's what forms your clouds. So the way I always remember that is the word C for condensation and C for cloud. And you could throw in C for cool. So you got three C's there. It cools, condenses, forms clouds. And all of that goes together in the process of cloud formation. The air has to rise, and again, as it does, it cools, it condenses, and it forms clouds. Now, clouds are water droplets, but they need something to stick to, right? A water droplet just can't form in the air magically. There has to be something for it to attach to. They call that in the world of meteorology, it's called condensation nuclei. So you need a small little dust particle, and then the water droplet will cling to that. So if you were to take a cloud material, let's say you went up in the air, scooped up some cloud material and looked at it under a microscope, right in the center, right there in the middle, would be a dust particle right there in the center, and then a water droplet would be sticking to that little tiny piece of dust. Right? In the atmosphere, there's billions, trillions of dust particles all floating around up there, and so in that cloud, there's going to be all these water droplets with little tiny dust particles at the center of each droplet. So they call that a condensation nucleus, or in plural would be condensation nuclei. So those are dust particles that the water would stick to. So just remember the three C's. It has to cool, condense, to form clouds. Now, the colder air, that's higher up. The word that meteorologists will hear them often say, above us, way up in the atmosphere, we have what's called a loft. Cold air is a loft. Some of you might have a loft in your house. A loft is like an upstairs second floor, but it's like a balcony that you can look down into the living room or dining room of your house. You can look down to the first floor. And so when meteorologists say we have cold air aloft, they mean we have colder air higher up above us. Well, cold air, as you're aware, is more dense, right? So it's heavier, and heavier stuff sinks. So that's what it's going to start to do. It's going to start to sink. As it's sinking, it's going to do the complete opposite of the warm air. Remember, the warm air was going upwards into lower pressure. Well, now the cold air, because it's coming down and it's sinking toward the ground, is moving into higher pressure. So the pressure is going to increase. You're going to cause the molecules now, instead of moving apart from one another, you're going to force the molecules closer together, which makes more collisions. So it's just the opposite of rising air. Sinking air is going to collide. The molecules are going to hit into one another, start smacking around. That's going to cause more friction. Friction creates heat, and therefore the temperature actually gets warmer. So sinking air does the complete opposite of rising air. Rising air expands and cools. Sinking air, they usually say the word compresses, right? Gets squeezed together and heats up. The best way to show this is with a bike pump. If you have a tire pump, and if you use a tire pump, when you press on the tire pump, you have both going on. Inside the cylinder here, inside the bike pump, the air is getting squeezed together. So if you were to use a bike pump and just kind of keep pumping for, give it 30 seconds to a minute, and then put your hand on the cylinder, it'll actually get warmer because you're compressing all that air inside the bike pump, so it's getting hotter. But then let's say while you're actually using the bike pump and pushing on it, feel the air coming out of the nozzle. That air is coming out of that little nozzle and expanding. And as it's expanding out of that nozzle, it's getting colder and colder. So you can feel cool air coming out of the nozzle, but the cylinder inside is getting warmer. I have a link right here. I'll share that link on my on Canvas, so look for this link. These are YouTube clips. I have to be very careful with copyright issues. I ran into that last week. I was telling some of the students in class, I can't put YouTube videos inside my video because of copyright issues. And so I will put a link in Canvas so you can watch some of these YouTube clips. So this one right here, this is a link when you have these little like earth-looking icons. I'll put that on Canvas. This one shows how a cylinder works in a bike pump, whether the air is expanding or compressing. So I'll put that on Canvas. Now, when the air is cooling and it's turning from a gas, I'll put G for gas, back down to a liquid. And this is something we talked about in the last unit, topic 4. You're turning a water vapor back into liquid droplets. You are changing phase. And again, this was one type of heat we talked about in the last unit on topic 4. The type of heat used to change phase is called latent heat. And so latent heat is going to be released because you're going from a gas to a liquid. You're cooling the water vapor down, and so you're going to take the joules. Remember we talked about joules of energy? In the case of condensation, it's 2,260 joules of energy for every gram of water vapor. So for every gram of water vapor, as you're forming a cloud's forming in the air, that's going to release a lot of energy. 2,260 joules of heat per gram of water vapor is released. And so that's going to be now the driving force behind a storm. And that's I have this on the next slide. So students will say, well, what is that latent heat used for? When a cloud's forming in the atmosphere, Mr. Rocco, and you've got all this energy now, this heat being released during the process of condensation, what is that heat used for? Right here, supercells and thunderstorms. So it says supercells and thunderstorms occur where warm, moist air meets cold, dry air, suggests a source of energy for thunderstorms and tornadoes. Latent heat is in the warm, moist air. Latent heat, again, is not detected with a thermometer. It's, again, energy that, as the cloud is forming, is being released, and that's like the fuel to cause a thunderstorm to grow bigger and stronger, or a hurricane to go from a Cat 1 to a Cat 5, or the storm we have coming in now that you'll notice if you've been watching the weather like I have, being a weather geek. We started out where we weren't going to get much, maybe they said 2 to 4 inches, then it went to 4 to 8, 6 to 12. I think now, as I'm making this video on Sunday afternoon, we're up to 1 foot to 1.5 foot. I've even seen reports of possibly 2 feet. Now again, I'm on record here. As I record this, we'll see what happens with the storm. But as this storm starts to grow and build and become stronger and kind of park itself off the coast of Long Island over the next couple days, Monday, Tuesday, that's what's going to happen. As these clouds start building in this nor'easter, this thing becomes like a winter hurricane, so to speak, and that latent heat is all used to fuel this storm. This link right here, again, I won't put it on my video for copyright issues, but I'll share a link. This is kind of cool. You'll see when there's a hurricane, every 3 hours, they send in a hurricane reconnaissance plane. So one of these military planes will fly through the eye wall of a hurricane, and they take all the temperature readings, pressure readings, wind speed, etc. And it's really cool. It's a bumpy ride. It's a pretty scary job, but these men and women do this when they're keeping track of a hurricane. And so I'll post this video on Canvas. So get a chance, please watch this. It's really cool as you watch them bust through the eye of the wall of the hurricane, where the strongest winds are. The wall is always the strongest. And then once you'll see the plane goes into the eye, into the center, into the eye, and all of a sudden it's clear skies, it's beautiful, sunny, you know, picture perfect weather. But it's the wall that's the most, the scariest part of the hurricane. So I'll post this link right here on Canvas for you. Now, moisture is a little different when it comes to pressure. And it doesn't make sense. This is not common sense, right? If I said, hey, you know, Mr. Rocco's got a swimming pool in his backyard, and I want you to, you know, let's say it's summertime, and you're going to jump into the pool with all your clothes on, right? You got pants on, shirts on, everything. You're just going to jump right in. Forget about a bathing suit. Just jump right in with your clothes on, right? You're going to be like, look at me like, Mr. Rocco, you're crazy. Your clothes, you get out, right? Your clothes are sopping wet now. How do those clothes feel? Well, they feel heavy, right? They feel saturated because they're saturated with water. Or a sponge, right? If you take a sponge, you had, let's say, a dry sponge, and then run it under the faucet, and now feel the weight of that sponge after you've run it under the faucet, right? It feels heavier. However, when you add more moisture, again, we have a snowstorm coming in. We're going to get buried in a lot of snow over the next couple days. That's a lot of moisture. But what's coming is not a high pressure. And if you look on a weather map, what you're going to see is a big red L, which is a low pressure. So I'm trying to color it in with my mouse. But anyway, you look on a weather map and you see a big red L, low pressure system. And the lower the pressure, the stronger the storm, the more moisture it has to work with, which is complete opposite of your clothes or a sponge. Again, if you jump into a pool with your clothes on, your clothes feel heavier, right? Which feels like more weight. If you soak a sponge under the faucet, it feels heavier, right? More weight. But actually adding more water to the atmosphere, adding more moisture, actually makes the air lighter. It makes it less dense and less pressure. So it doesn't feel, it's not actually heavier, it's actually lighter. Low pressure. So low pressures are storms. There's a lot of moisture with low pressures. And I was referring to that last week on one of the assignments. Some of you missed it. It was a question that said what kind of weather is typically with a high pressure. And the way I always remember high pressure, when you look on the weather map and you see a big blue H, high rhymes with dry. And when do you usually have dry skin? Wintertime, when it's cold out, right? This time of year, January, February, you have chapped lips, dry skin, you need moisturizer, you have static. A lot of times we get shocked sometimes when you flip on a light switch in your house, especially if you have carpet in your house and you walk across the carpet barefoot and then you go to flip on a switch, you might get a little shock. The air is very, very dry in your house, especially because you're heating your house, and heating your house always dries the air out in your house. So high pressure is dry. High rhymes with dry and cold, all right, heavy air. Low pressure is warm, but it's also more moisture. And again, why that doesn't make sense? I know you might say that doesn't make sense. Shouldn't more moisture in the air make the air higher pressure, like heavier? And let me explain why. It has to do with molecules and what's called the atomic weight. Atomic weight is actually weighing an atom. How many atoms, how many protons, neutrons, all the stuff that's in an atom, and therefore figuring out the weight of an atom. And this gets into a little bit of chemistry, which is never my specialty, but in this case it is when I talk about air pressure and moisture. So if you had dry air would be air without any water in it. The air that you breathe is 78% nitrogen and 21% oxygen. The nitrogen that you breathe in is N2, nitrogen 2. It's 2 atoms of nitrogen. Now, if you look on the periodic table, right, you've probably seen that in middle school. You guys did a little chemistry, probably Miss Kogel. Nitrogen's atomic weight is 14. you breathe in nitrogen 2, which means 14, you double that. 14 times 2 gives you nitrogen 28. That's what you're breathing in all the time. Nitrogen atoms that weigh 28. Oxygen, you're breathing in not just O, but O2, which means 2 atoms of oxygen. Again, if you look up on the periodic table, the atomic weight of oxygen is 16. But if you're breathing in O2, that means 2 times 16, you're breathing in 32. So when you're looking at dry air, the air that, let's say right now, it's cold outside, it's not snowing yet, so the air outside on this Sunday afternoon is dry. The air is going to be made up of nitrogens that weigh 28 and oxygens that weigh 32. Mostly. 78% nitrogen, 21% oxygen. The rest is ozone, carbon dioxide, there's some argon in the air, but most of it is nitrogen, oxygen, weighing 28 and 32. Now, if you have a storm coming, like we do have, we're going to start to build moisture into the atmosphere. That's water. Well, let's take the chemical formula for water. Water is H2O. Hydrogen has an atomic weight of 1, if you look it up. So you have 2 hydrogens. So if each hydrogen has an atomic weight of 1, 1 times 2 means 2. You have 1 oxygen, which we talked about before. In water, it's not O2, it's just O. So there's only going to be 16. So you're going to now take a water molecule, 2 hydrogens give you 2, a weight of 2. 1 oxygen gives you 16. 16 plus 2 is 18. You see, I have that down here in my notes. So a water molecule has a weight of 18. Again, dry air without any moisture is nitrogen, oxygen. Each of these respectively are 28 and 32. So here's what has to happen. When a storm rolls in, like it is today, tonight, and tomorrow, every time you bring in a water molecule, you are putting in something that has a weight. Let's say this is the air over here. You're putting in something that has a weight of 18. But in order to fit that water molecule in, you have to do what's called substitution. I compare this to basketball, right? There's always 5 players on a court. If you want to bring somebody in, you got to take somebody out. You can't add a 6th player. You have to always have 5 on the court. So somebody goes in, but somebody has to come out. Well, think of the air in the atmosphere like a basketball court. There's only so much room for molecules, whether they're water molecules or air molecules. There's only so much that can fit. Well, when a storm's coming and all that moisture, every water molecule going in means you have to take something that else was in there, which was dry air, out. So that means, and typically it's going to be the nitrogen because notice the air is made of 78% nitrogen. So majority of the air is nitrogen you're breathing, which means most likely a nitrogen's coming out. Well, that nitrogen is 28. So what does that mean? I hope you see where I'm going here. You're putting in a water molecule that weighs 18, but you're taking out a nitrogen that weighs 28. So wouldn't you agree with me that you're putting in something that weighs less, right? This only weighs 18 water, and you're taking out nitrogen, N2, that weighs more. You're putting in a lighter thing, you're taking out something heavier. That's why the air becomes less weight or less pressure when there's moisture in the air, which again doesn't make any sense because you think about a shirt or your clothes, again, like you said, jump in a pool, but fabric works differently, right? When you jump in a pool, it's not that a piece of your clothing gets ripped away and then make room for water. It's a little different. The water molecules can fit between the fabric molecules. So that's a little different. You don't have to substitute when you soak a sponge. You don't have to substitute when you jump in a pool with your clothes on. But in the air, it doesn't work that way. There's only so much space for molecules, whether it's water or air. In the case when water comes in, you have to take out something else. There's only some X number of space there or whatever, and so water is going to weigh less and you're taking out nitrogen, which weighs more. And so actually when a storm comes in again, that's why you're looking on the weather map, you're looking for the L, the low pressure, so it's less weight. The air becomes lighter when a storm comes in, whether it's rain or snow. In this case we're going to have snow, but still moisture, whether it's frozen or liquid form, doesn't matter. So the air will become lighter. And if you look at a barometer, and probably look at one today and actually keep track of it, go on over the next day or so and watch the pressure. You can go online, look at the National Weather Service, Google, go to the Weather Channel, any one of the news sites, and they will show you, and maybe even watch the news. They'll talk about, the meteorologists will talk about the pressure. The pressure is dropping as the storm comes in because all that moisture is heading our way. So hopefully that was a long explanation, but hopefully that makes sense. This shows it in a picture form. So let's say these green circles are dry air molecules. These could be N's. This is an N. Well, N2, remember. These are N2s. And these could be O2s. All right, O2s. All right, and again, these weigh 28. The oxygens weigh 32. But then down here, let's say a storm's coming. You're adding moisture now. Water weighs 18. So you're going to put in an 18. You got to take out something here. Let's say nitrogen that weighs 28. So 18 goes in, 28 comes out. Something that weighs less is going in. Something that weighed more is coming out. And therefore now lighter things are going into the air. Heavier things are coming out. And that's why when it's raining and snowing, the air becomes lower pressure, less dense, less weight, lighter. Baseball, and I love baseball, follow baseball, been playing baseball since I was a kid. If you ask a baseball player, believe it or not, or take a pro baseball player, what's the best weather to hit the ball further? Actually, the best weather is a warm, sticky, humid day. Now, you might not want to play when it's hot and humid outside, but the ball, as you can see here, optimum for long baseball hits. High elevation is also good because less pressure, right? So if you follow any of the sports teams, the Colorado Rockies, right, they play up a mile up in the Rocky Mountains. So you're at high elevation. Well, the higher elevation you are, the less pressure there is up there at place like Denver, where the Rockies play. And so the ball will even go further. There's what they call less frictional drag. The ball isn't being pulled by the weight of the air because the air is actually lighter if you're in Denver as opposed to New York City. You want, obviously, the wind to blow out, not toward home plate. And again, you want a warm, sticky day because, again, warmer air, the molecules spread out. And again, more moisture makes the air lighter, not heavier. So you ask a home run hitter and they say, hey, today it's a really hot, humid day. They know right away when they come to the ballpark, they're going to be hitting, the ball's going to go pretty far that day. The outfielders have to know they got to play deeper in the outfield. You got to play much further out on a hot, sticky day because that ball's really going to sail that day. It's going to fly. Opposite would be cold and dry, right? A cold, dry day. Remember, cold and dry is high pressure, right? High rhymes with dry, and usually cold air. And so on a cold, dry day, the outfielders could take a few steps in toward home plate. And I remember that playing baseball for Rhinebeck, because I went to Rhinebeck, as you know. And I remember the coach would tell, the outfielders, I played center field, and he'd tell us, Mr. Argo, take a couple steps in. And we take a couple steps in. The ball wasn't going to go that far on a cold, dry day. And if the wind was blowing in, that helped. Low elevation, again, would help. So those are all factors that are going to affect the baseball. And that could be any sport. You could be talking about football. I mean, you got the Super Bowl next weekend. They're playing in Tampa, Florida. If it's a warm, humid day next Sunday, Tom Brady and Patrick Mahomes are going to really be able to chuck that ball. It's going to go pretty far if it's a hot, sticky day. If it's a cooler, drier day, no. But if it's a warm, humid day, which typically Tampa does have, you're going to see that ball be able to sail pretty far. They're going to have a much easier time getting some pretty long passes during the Super Bowl. So you have to watch for things like that. So yeah, weather has a big effect, obviously, on a lot of things, including sports. So to sum up the differences, low pressure, again, lighter air is when it's hot and it's sticky, warm, hot, moist, stormy. Right? Again, low pressure. Other way I remember low pressure, think of, I feel kind of low today. I feel kind of sad because it's stormy outside. As a little kid wants to go outside and go ride his bike or her bike, skateboard, something like that. You can't because it's cold. It's rainy out. It's warm, sticky, and it's raining. High, again, rhymes with dry. That's why I remember that. And again, think of when you have dry skin. Oh, yeah, cold. In the winter, my skin tends to be drier. But sunny. So like yesterday, I know Saturday, it was cold inside the house. If you looked out the windows, I was looking out the window. My wife's like, "Oh, it looks like a beautiful day." I said, "Yeah, it looks nice. Looks are deceiving. It was a cold, clear blue sky, but definitely high pressure." And one more slide. So as you go up, right? Remember I was talking about Denver playing for the Rockies. As you increase your altitude, you go further up, the pressure and the density both decrease. Less pressure as you go up. And again, as temperature and moisture increase, well, warm, sticky day, warm, more moist, more humid, also density and pressure decrease. So in both cases, these are inverse relationships. Altitude increases, the density of the air and the pressure of the air decrease. As you add more temperature and moisture to the air, the density and the pressure of the air decrease. So both of these are inverse relationships. And that is it for this video. There'll be one other video this week. I'm going to make 2 for the week and a few assignments. So look for all that on Canvas. And I will talk to you soon.